Hello, learners of mathematics. Welcome to session 2 of Unit 1 Mappings and Binary Operations. In the previous section, that is session 1, we describe a mapping and we also state the differences among the various classes of mapping. If you remember, we describe injective mapping, surjective mapping, and bijective mappings. In this section, you'll be learning how to combine two mappings to form a new single mapping. In that matter, session 2 of Unit 1, we are looking at composition of mappings. Okay, by the end of this section, you should be able to combine two mappings to form a single new mapping. Good. Composition of mapping. What is composition of mapping? Let's look at this definition 5. Composition of mapping. Suppose that f is a function. Let's take the mapping of x to t and g, and so take t to u. Then f followed by g, and that's how it's been written. Gov of x. That's g of f of x. G of f of x is given as g put inside the function f for all x in x. So once you put the function f into g, then you get that composite function of g of f of x, and that's what we call composite function. Note that the mapping on the right, that is applied first. So when I have g of f of x, g of f of x, then we say that gov of x, the mapping that apply first is f. So f followed by g, f followed by g. Good. Let's look at example. Let's look at example 10 of unit 2. Let the mapping f and g be as given in the arrow diagram below. You can see that f is a mapping from x to t and g is a mapping from t to u. That is, we want to find composite function g of f of x. G of f of x. So let me write it here. G of f of x is same as g you put inside the function x, f of x, and that is, I go to the diagram, I have my g here, then I have my f of x maps to 2, then I can say that g of 2, and g of 2 is also maps to c, then I can say that c. Similarly, you can also find g of f of y, and that is, you get g of, look at the y, maps to 1. So g of 1, and that gives g of 1 also equals b. Similarly, g of z, g of z equals, okay, g of z, that is, the bracket is very important. But when you ignore it, it's not wrong. You may decide to ignore, but make it there so that it look very nice. Okay, so you get g of z, and then that is 3. F maps to 3, and then g of 3 also maps to what? A. Maps to A. Okay, let's look at the next example. This is the next example. Let f be a function from real number to real number, and g be a function also from real number to real number. Defined as f of x equals x squared plus 2 and g of x equals x minus 1 respectively. Now I want to find the functions, composite functions, f followed by g and then g followed by f. Then we draw conclusions. Now let's start. The first one is g. Let me take the pen. G of f of x equals g, you put in inside the function f of x, that's x squared plus 2. That is, any place you see x in the g, you put in x squared plus 2, and that gives me x squared plus 2, and then there's already minus 1 there. Simplifying this, what do you get? You get x squared plus 1. X squared plus 1 for the function g of f of x. Okay, we look at the next one, that is f, and then we are going to put inside g of x. So I get f, put inside g of x, that is wherever I see x inside f, I put x squared, x minus 1, x minus 1. So this will be equals to x minus 1 squared plus 2. Because there is x here, I put inside x minus 1. And when I simplify this, you get x squared minus 2x, yes, plus 3. Plus 3 as your final answer. Now, what conclusion can you draw? You can see that g of f of x is not equal to f of g of x. Good. Let's look at the next example. Given that f of x equals x plus 4 and g of x equals x minus 4, now I want to evaluate fork of x, g followed by f. Now I put inside x minus 4 into f of x. So you are going to put this function here. So I get x minus 4 plus 4. And what is the answer? I'll get x. The same thing here too, you put golf. You put f of x into x minus 4. Wherever I see x, I put f of x there. So I get my x plus 4, then already minus 4. And the answer is what? I get my x. I get my x. Okay. So you get your x here. Good. I mean, right? So get your x. Okay, they place small. So we leave it like that, and then we say that that is my x. That's my x. So what conclusion can you draw? You can see that here fork of x equals to golf of x, and then the answer is x. All give the answer x. But this one is not always, please. Not always that it happens. Not always that it happens. Sometimes it can happen. But in actual fact, golf is certainly not always equal to 4. Good. Let's look at the next slide. Golf and fork, g of f of x and then f of g of x are not always the same. Now let's look at these theorems. Theorem 1. Suppose that f of x is a function from s to t and g of x is a function from g to t are two mappings. Now the theorem states that A, if f and g are onto mappings, then the composition g of f is also onto mapping. Again, if g of f of x is onto mapping, then g is onto mapping. How do you prove? Let's see how to prove for the first part. Okay, so since g of f is a mapping from set x to set u, then let's let u be a subset of u, small u be a subset of u, that is this small u to be a subset of u. Then we can say that, and on the assumption that g is onto mapping, then there is this t also a subset of the capital T such that f of x equals t. Now for u being a member of u, then it follows that there exists s also a subset of capital X such that the composite function g of f of x is actually equals to g, take input of f of x and it goes to g of t, and the result is u. So when you draw arrow diagram, this is very clear and so simple. and that is the proof for A. For the B, it's so simple, and you can read the proof from your course outline or your course material. So simple. Great. Okay, let's take the example. If f is a function from natural number to natural number defined by f of n equals 2n, and also g of n also taking a natural number to a natural number, and g of n is also defined as a piecewise function, that is odd, n plus 1 on 2 and then n on 2 if even. Now we want to show that g and g of f are both onto mappings, but f is not. Let's show that. So first, let's show that g is onto mapping. Okay, so if we believe that small n is a member of this big N, is a member of natural number. Good. If n is even, then we can say that 2n is also even. 2n is also even. Once n is even, 2n is also even. Okay, you know that 1, 2 is multiplied by every number. Actually, the result is even, whether odd or even number. Okay, if that's the case, then g of 2n, once it's even number, it means that you put it into where it's even, and the even is here. G of 2n will be equals to 2n on 2, and that will be equals to n. Great. Also, if n is odd, then guess what will happen? If n is odd, it implies that 2n minus 1 is also odd. Because you know that when you have odd number, you multiply by 2, you get even. So when I take 1 out from that, I get odd. Then let's see g of 2n minus 1. Actually put that one into where we have the odd here, and that is 2n minus 1 plus 1, and the answer is you get n. You get n. Okay, so since one is odd is defined and one is even is defined, then this implies that g is onto mapping. G is onto mapping. For g being onto mapping, and it implies that the composite function g of f is also onto mapping, and the reason is that the identity mapping is onto. Once the identity mapping is onto, definitely the composite function g of f is also onto mapping. Certainly f is not onto, and the reason is that odd positive integers are not defined. Odd positive integers are not defined in f. And when we look at f equals to 2n. So if it is 1, what do we get? If it is 2, what do we get? So it means that the odd positive integers do not have images. They are not having images. Good. So this is just simple for this example 14. Let's look at theorem 2. Suppose that f is a function that takes s to t, and g is also a function taking t to u are two mappings. Then this theorem also states that if f and g are 1-to-1 mapping, then g of f is also 1-to-1. And if g of f is 1-to-1 mapping, then f is also 1-to-1. This proof is very simple and very easy, I think self-explanatory. So I leave this proof for you to do it, and it is also in your course material. So in this session we looked at composition functions, that are composite functions, and we said that when you add two functions to form a new one, then we get what we call the composite function. And remember, we also said that the g of f is not the same as f of g. They are not always the same. Okay, so thank you very much. And then in the next section we want to look at inverse of a mapping.